Hello and welcome to a new video on cryptography for everybody. In today's video, we will have a look at a GDR spy cipher developed by the Stasi. And the cipher's name is GRANITE 160. I structured this video into 6 different parts. In the first part, we will have a look at the background of the GRANITE 160 cipher. In the following, we call this cipher only GRANITE. Then we will have a look at the Günter Guillaume case. Günter Guillaume was a GDR spy who was near Willy Brandt, the German chancellor, and he was discovered and he used the GRANITE cipher. Then we will see how the GRANITE cipher works. After that, we will have a look at the key generation and message setup of the GRANITE cipher. Then we will have a look at the security of the GRANITE cipher. And finally, of course, we will do it in CrypTool 2. We will encrypt and decrypt using the GRANITE cipher. GRANITE cipher is a hand cipher which was used for communication between the GDR's Ministerium für Staatssicherheit, in English Ministry for State Security, or abbreviated MFS, or also known as Stasi, and their agents in West Germany. You can see the logo of the MFS here on the right side. This is taken from Wikipedia. And the GRANITE cipher is described in the Geheime Dienstvorschrift. This is English for Secret Service Regulation, GVS 1064/59 and GVS 1065/59. And the cipher is a variant of the Doppelwürfel, which you probably know as a double columnar transposition cipher. The communication with the agents that use the cipher was done via number stations. We already had a video about number stations on this channel. So the agent had to turn on his radio and wait for his call sign. And then the agent notes down the numbers and then he decrypts the numbers using GRANITE. But the West German Zentralstelle für das Chiffrierwesen, English Central Office for Ciphering, was able to capture and decipher messages because they could guess some of the used keys of the GRANITE messages. Now let's have a look at the Günter Guillaume case. Günter Guillaume and his wife Christel were East German Stasi spies. And Guillaume became officer in the Economic, Financial and Social Policy Department of German Chancellor Willy Brandt. You can see Günter Guillaume here on the right side in this picture and Willy Brandt, the German Chancellor of the time, also in that picture here. This picture is around 1973. The Guillaumes used, as I already said, the GRANITE cipher. But the West German Zentralstelle für das Chiffrierwesen was able to decipher messages. Matching birthday date wishes and well wishes for the birth of a son were found in a deciphered message. And because these matched to the dates of the Guillaumes and their son, they were caught and arrested in 1974. Ironically, the mentioned birthday dates of the Guillaumes were not their actual birthday dates, but their agent fake birth dates. Despite having good evidence, police raided his home, but Guillaume instantly confessed being a Stasi spy when approached by the police. Now let's have a look at how the GRANITE cipher works. The GRANITE cipher is a hand cipher and you have to perform a few steps. I put these 5 steps here on the slide and later we will have a look at each step individually. The first step is to create a straddling checkerboard based on a keyword. This has to be done to convert from text to digits. Then we encrypt the plain text using this straddling checkerboard. After that, we create 2 rectangles for the double columnar transposition cipher based on 2 key phrases. Then we encrypt the numbers which are the result of the encryption of step 2 using the first rectangle. And then we encrypt the numbers again. This is a result of step 4 using the second rectangle. These 2 steps form the double columnar transposition cipher. Let's have a look at each step on its own. First, we have to create a straddling checkerboard based on a keyword. we write down such a checkerboard, and then we write a keyword into the straddling checkerboard. And in this example here, and by the way, all the examples that are used in this video are originally Stasi examples from the original Stasi documents. So these are also in German. We use here the example keyword Rheinast. This could be translated to Rhine branch. You write the keyword into the checkerboard, Rheinast, and you of course omit writing a letter more than once. Then you fill the remaining part with the rest of the alphabet. So B, C, D, and so on is the rest of the alphabet. And then we have three special symbols. We have the ZS, we will see later what this means, then a full stop and a comma. Let's encrypt an example plaintext using the straddling checkerboard. And our example plaintext is: Jeder Zwischenfall bei Unternehmen Edelweiss am 12. März ist möglichst zu vermeiden. Bericht bis 1. April. The English translation here is: Any incident during Operation Edelweiss on March 12 is to be avoided if possible. Report until April the 1st. The first step here, before we can encrypt, is to clean up the plaintext. To do so, we replace every occurrence of J by 2I. If we want to encrypt numbers, we actually don't encrypt these in this step. We just write this ZS. ZS is Zahlensignal. This is German for number signal. Then we write the number 3 times the first digit, 3 times the second digit, and so on, followed by a ZS again. So we replace the 12 here by this part here, the first here by this part here. Then we have to encrypt each letter. Let's start with the I here. The I is encrypted by a 3, so we write a 3. The second I here is also encrypted by the 3, so we write a 3 again. Then we have the E. The E is the 2 here, as you can see here, so we write a 2 here. Then we have to encrypt the D. The D is 82, so we have to write the D here. And we continue and go on and on and on. Here you can see that we just write the ZS. The ZS is the 97 here. We write the 97 here. Then the 111, the 111, the 222, the 222, and then again the 97. So we encrypt our cleaned plaintext using the straddling checkerboard. In the next step, we have to create 2 rectangles for the double columnar transposition cipher based on 2 long other key phrases. And here we have 2 example key phrases and 2 example rectangles. We have Gute halten, ich bin gewiss, this is English for give credit, I am sure. And then, dass der feinste Mann, in English, that he is the finest man. Where we obtain these key phrases we will learn later, but first let's see how we use the key phrases. We write down the key phrases in the rectangles letter by letter, and then we assign numbers to the letters. And we go from left to right through the letters, and we search, for instance, for the A. The first occurrence of A is 1. Then we continue, we find a B, we write a 2. So we go through the alphabetic order here and write the numbers below the letters. For instance, the 4, we come to the end here, then we start again here, and then the E here is the next letter, so we write the 4 here. Then we have a second E here, we have to write 5. So you have to increment the number each time. Here's the third E, we have to write a 6. Then we are at the end, we have to start, then F, we have no F, G, we have here the 7, and then we have a second G here, we have the 8, and so on. And we prepare these 2 rectangles based on these key phrases. Now let's use these for encryption. We first encrypt the numbers which are the result of step 2 using the first rectangle. We just take the numbers that we have created, we write the numbers from left to right, from top to bottom into our rectangle. And then we read out the numbers column-wise based on the numbering here, and the numbering was based on our key phrase. So we start with the first one, with the first column here. We write 223061. This is 223061. We go to the second column here, 949871. 949871, and we continue reading out the rectangle column-wise until we reach the end. This is a single columnar transposition cipher. Then in the fifth step, we encrypt the numbers again. We take the result of step 4, we write these row-wise into the rectangle, and again we read out column-wise our ciphertext. So we have 2523288 here. So we have 2523288 here. Then in the second column, 967459, 967459. And then we continue. This 2 here actually is wrong here. This is not part of this column. This should be part of the third column here. Yeah, here's the 2. That's the 2 here. And we go on and on and on, reading out our columns until we obtain our final ciphertext. So we have now encrypted the text with a straddling checkerboard and 2 times with a columnar transposition cipher, which is a double columnar transposition cipher. Now let's have a look how we generate a key and how we set up our message. The Secret Service Regulation describes several rules how to generate a key and how to indicate how we created the key so that the receiver can create the same key using a so-called Kenngruppe or English indicator group. And the correspondence, the agent and the Stasi agree in advance on 3 different things. First, they agree on a book, then they have to agree on a secret keyword, and they have to agree on a secret 5-digit key number. For example, 65792. This is also an example taken from the Stasi. Then the straddling checkerboard is created using the secret keyword. The plaintext, before we encrypt it, has to be cleaned. We already saw that when we encrypted the plaintext. We replace the J's, we replace the umlauts, so an A becomes an AE, an Ü becomes an UE, and so on. We have to add number signals, we have to repeat the digits of the plaintext 3 times, and so on. And the number of digits of the ciphertext has to be divisible by 5. This is a rule of the Stasi. I think that they invented this rule because they always send messages in groups of 5, but I'm not sure. It's not written in the Stasi documents. And if it's not divisible by 5, we have to add nulls. So just add some random numbers until we can divide our digit ciphertext by 5. Then we have to take 2 key phrases from the book, and these are the keys for the double columnar transposition cipher. So the agent and the Stasi have the same key book. And each phrase that we take from the book has to consist of 5 words, and the total number of letters of each of these phrases that we use for the double columnar transposition cipher have to be 15 or larger. The phrases are taken from a random line of a random page. So when you want to encrypt using the book, you want to create the phrases, you just open the book at a random position, then you choose a random line and you take the first 5 words as first key phrase and the last 5 words of the same line as the second key phrase for the columnar transposition cipher, for the double columnar transposition cipher. The length of the key phrases have to be different. If not, we have to append the first letter of the second phrase to the end of the second phrase. And the second key phrase length must not divide the text length. Now let's create our final message that we can then send. So we have our created ciphertext from the encryption, and we have to add the indicator group so that the receiver knows how to decrypt this ciphertext. To do so, we create a 5-digit number from the used page and line numbers from the book that we used to obtain our key phrases. For example, we used page 129, and there's a second line. This becomes the number 129, this is a page, and then 02 for the line. We add our 5-digit number with the 5-digit key modulo 10. You know this 5-digit key is known by us and by the Stasi. So we take our computed number or generated number here, we add our secret 5-digit key modulo 10 and we obtain this number here. And this is the indicator group. So for example, 2 plus 2 is 4. 0 plus 9 is 9. 9 plus 7 is 16, but we have to compute the modulo, so we get 6. 2 plus 5 is 7, 1 plus 6 is 7. And the receiver now could add the same number again, could subtract the number using modulus and obtain the page and line information to create also the key phrases. We add the indicator group 2 times in front of the final message. So our final message looks like this. We have 2 times the indicator group 77694 here, and then we have our ciphertext. And as you can see, we divide our ciphertext or our message into groups of 5. Now let's have a look at the security of the GRANITE cipher. And there are additional rules invented by the Stasi. The minimum message length has to be 50. If not, we have to add nulls to the message. And the maximum message length is 400. If the message is longer, we have to separate it into different messages. The used book that we in the Stasi use has to have a minimum of 250 pages. And there are many more rules how to reorder plaintext, handle the books, so that the book does not look too new or too used, and so on. You can find this in the original Stasi documents. Now let's compute the key space size of the GRANITE cipher. The key space size consists of 2 parts, the straddling checkerboard and 2 times a single columnar transposition cipher, which is a double columnar transposition cipher. The straddling checkerboard's key size, when we only change the alphabet letters, is 25 factorial, because we have 25 letters for the first letter to choose from, 24 for the second, 23 for the third, and so on, and this is 25 factorial. This is about 2 to the power of 83.68 for the straddling checkerboard. Then, for a single columnar transposition cipher, and here we use key length from 15 to 30, we can also compute the key space size. For a key of length 15, we have 15 factorial, then for a key of length 16, we have 16, for 70, 17, and so on and so forth, and for a key of length 30, we have 30 factorial. And in this case, we have to add all the key length. And the result is 2 to the power of 107.76. Now we can compute the total key space size. It is the key space size of the straddling checkerboard multiplied the key space size of the single columnar transposition cipher, multiplied again, because we have a double columnar transposition cipher, with the key space size of the single columnar transposition cipher, and we obtain a total key space size of 2 to the power of 299.2. This is very impressive. Then we can compute the unicity distance. Remember, the unicity distance is the minimum number or the minimum length of the ciphertext that we have to obtain only a single valid solution when we perform cryptanalysis. And we can compute the unicity distance by dividing the entropy of the key space by the redundancy of the language. The entropy of the key space is exactly this exponent here, 299.2, divided by 3.2. This is the redundancy of the language. And the unicity distance is then about 93.5. This means we have to have a message of a minimum length of 94 to obtain, or to have the chance to obtain, only a single valid solution. And to be honest, this cipher is even today a very, very, very secure hand cipher when used with good keys. And the Guillaumes didn't use good keys, so the West Germans were able to guess the keys and because of that to decipher the messages. If they would have used random keys, they could have not been broken probably in that time. Now that we know how the GRANITE cipher works, let's encrypt and decrypt using the GRANITE cipher component of CrypTool 2. I'm here now in the Start Center of CrypTool 2 and I want to show you how you can use the new GRANITE cipher components that we have implemented in CrypTool 2. And we will build our own workspace. We click on the Create New Workspace button here and get an empty workspace. Then we search for GRANITE Cipher. In German, GRANIT. The E is missing in German, or in the German name. Then we copy this 2 times because we want to encrypt and decrypt. Then we need text input here. This will be our plain text. This is a test of the GRANITE Cipher component of CrypTool 2. And we connect this with our Cipher component. Then we connect this with the second one. And then we need a text output for our ciphertext. This is our ciphertext, and we copy this, and this here will be our decrypted plaintext. Now we need a total of 3 keys. We need the keyword 1, which is used to create the threading checkerboard. Then we need the keyword or key phrase 2 and the keyword 3. These 2 are used for the double columnar transposition cipher. Biggest width. So this is keyword 1, 2, and 3. I hope this is not, that I'm not in the way. So let's put the second here and the third here. We connect the first keyword component or text input component with both components. Then we connect the second one with both, and the third one. Then we shouldn't forget to change the GRANITE Cipher components to encryption. So the first is encryption and the second has to be set to decryption. And then we need keywords. Let's choose secret keyword for the threading checkerboard. First key phrase or secret key phrase for the second keyword, and another secret phrase for the third keyword. This is the third keyword. And now let's test if the component works. And as you can see here, we obtain a digit ciphertext. So the first GRANITE component first used the threading checkerboard and then transposed it 2 times using the double columnar transposition cipher. And the second component was able to decrypt our ciphertext using first the double columnar transposition cipher and then the threading checkerboard. The component has one nice feature that we also added, and this is the add nulls feature. If I click this here and encrypt again, and this is a bad example, I have to add something like an A here. So I added the A after the 2, and you can see that we have the 2 here. So that's also a nice feature of the GRANITE cipher. It allows the encryption of numbers. But as I said, here we have now an A. But you can see that in the decrypted ciphertext, we have now here KWR. And when I just enter an A again, you see that the letters that follow the A always change. And that is because we enabled the add nulls check here. And that means that if our resulting ciphertext is not divisible by 5, it automatically adds random letters to the end of our plaintext here. By the way, if you want to see the ciphertext in blocks of 5, we can just easily add a string operations component here. And then we can change this to the block mode. Operation is block. And then we should see blocks of 5 here, yes. And you can see when I type here, we will always have blocks of 5. But when we disable the add nulls here, and now we add a letter here, you see it can also be a shorter block. Yeah, and this is everything that I wanted to show you in this short video. I have shown you the GRANITE cipher, how it works. I've shown you the story of Günter Guillaume, the East German spy who spied for the GDR with Willy Brandt. And yeah, you could now download the current version, the current nightly build version of CrypTool 2 and use the GRANITE cipher on your own. I hope you liked this video. If yes, please give a thumbs up. Also, if you did not yet subscribe to this channel, please do so. This really helps me to grow the channel and to make CrypTool 2 more popular. So thank you very much for watching and see you in the next video.